Europa is widely considered the most likely place in our solar system beyond Earth to have life right now.
It's a moon, an icy world orbiting Jupiter.
Beneath its icy surface, a global ocean of water. Everywhere on Earth that there's water, there's life. So we want to understand, could Europa be a place where life might exist today?
3, 2, 1, lift off.
Europa Clipper is the first mission dedicated to exploring Europa.
This is the largest interplanetary spacecraft NASA has ever built and launched.
We have the right team, the right technologies to leverage to go to Europa now and unlock those mysteries that are just waiting for us.
The pictures we're going to get from Europa Clipper are going to blow our minds.
How could you not be excited about something as monumental as this?
Welcome to NASA Science Live. Today, we're pulling back the curtain on one of the most exciting space missions of our time, Europa Clipper, a mission that will explore Jupiter's icy moon, revealing what's beneath its surface. I'm your host, Tahira Allen, and I am so excited to be here with you today. Now, here's the best part. Today isn't all about us talking, it's about you. If you have questions throughout the show, send them in using the hashtag AskNASA on social media or drop them directly into the comments wherever you're watching. Okay, let's jump right in. What makes this mission so special? It's Europa, one of Jupiter's 95 moons that likely has a vast liquid ocean hidden beneath its icy surface. The Europa Clipper spacecraft will travel all the way to this mysterious moon to answer one big question. Does Europa have suitable conditions to support life as we know it? Today, I'm joined by two incredible guests from NASA's Jet Propulsion Laboratory who are helping make this mission possible. First up, we have Cynthia Phillips, Europa Clipper Project Staff Scientist. Welcome, Cynthia.
Thanks, Tahira. I'm so excited to be here today.
And Jenny Kampmeyer, Europa Clipper Science Systems Engineer. It is great to see you, Jenny.
It's great to be here, Tahira. Thanks for having me.
Yeah, thank you both so much for being here. Can you start off by telling our viewers a little bit about your roles at NASA? Cynthia, we'll start with you.
Sure. Yeah. So I'm a project staff scientist on the Europa Clipper mission. And that means I basically work to help the project scientist and the science team make sure that the mission has everything it needs to be able to accomplish its top level science goals and objectives. And I'm also a planetary geologist. So I'm really excited about getting to see Europa.
And what about you, Jenny?
Yeah, so I'm the science systems engineer for Europa Clipper, and basically what that means is that I sit kind of right on the boundary between science and engineering. So I work really closely with the science team, helping to kind of explain engineering constraints and how they might affect the science that we're going to take. And then I also work really closely with the engineering team to make sure that we're getting, the most science, the best science we possibly can with this incredible spacecraft. So it's a really cool job getting to kind of, help work really closely with these kind of two sides of the project.
Yeah, and Jenny, we actually spent the day with you at NASA's Jet Propulsion Laboratory, where Europa Clipper was built, to learn more about your role in the mission as part of NASA's Behind the Spacecraft series. So let's take a look right now.
It's a surreal experience to know that we're doing some really humanity-changing science with the spacecraft. My name is Jenny Kampmeyer, and I work on Europa Clipper, helping science fiction become science reality. Europa Clipper is NASA's flagship mission to explore a moon of Jupiter called Europa. It is our most promising candidate in the solar system to look for a habitable environment. So here's our Europa Clipper spacecraft being built to see something that's been on paper for so long actually here. That's an incredible feeling. I sit right on the boundary between science and engineering. Decisions that are made on the engineering side and decisions that are made on the science side often have effects on each other that we don't always see. And so my job is to kind of help make those two things work together. I have a bit of a non-traditional background. I play the flute and was a professional musician in New York City. And then I had a bit of a serendipitous moment and happened to see the last space shuttle launch. Had a lightning bolt moment of, I have to go do that. There are a lot of similarities between music and engineering. Playing in an orchestra, you are focused on what you're doing. You have to be listening to a different section and what they're doing. Then you have to all be watching the conductor for one performance that has to go flawlessly. To me, that's the same as working on an engineering team. We're all kind of moving towards the same goal that has to work because we get one shot at it. One of the reasons I ended up studying music is that I felt a little intimidated by the engineering program, where I was the only woman. And so that experience made me feel like I didn't belong there and that I couldn't do this kind of work. So I spend a lot of time working with all sorts of groups of people and students to let them know that they do have a place here, even if they don't fit a stereotype. I can't wait for Europa Clipper to get launched, and seeing it leave Earth on its way to Jupiter is going to be an experience I'll never forget.
So cool. I mean, seeing the making of this mission is always so impressive. For our viewers, if you would like to watch more episodes from this season of Behind the Spacecraft, you can visit go.nasa.gov/Europa Clipper BTS. Okay, let's dive into the details about why NASA chose to send a spacecraft to Europa. Cynthia, we know that life on Earth needs certain ingredients. Can you break those down for us and explain why scientists think those ingredients may also be present at Europa?
Yeah, so as you heard, Europa is this moon of Jupiter. It has this ice layer at the surface, but under that ice, there's this huge ocean of liquid water. And we're pretty sure there's more water there than all of Earth's oceans combined. And so water is really one of the key ingredients for life. And when I say life, I mean life as we know it, life that's here on the Earth today. It relies on liquid water. And basically, almost everywhere that we've found water on the Earth, we've found life there. And so we think that water is one of those key kind of ingredients for life. But you can't just have water. The second ingredient is the right chemical elements. So these are things like carbon, nitrogen, hydrogen, phosphorus, sulfur, oxygen. They're elements that are pretty common in the solar system. And so we're pretty sure that those exist on Europa in sufficient quantities. But then the third ingredient is an energy source. It would be really boring if all you had was this water, you had these chemicals, and there was no energy to drive chemical reactions, right? There's nothing that actually could happen. And so in the case of Europa, we think that what there is there's a couple possible energy sources. One is there could be hydrothermal systems. So these are vents of like superheated water at the bottom of Europa's ocean, where the water could circulate into the crust. You could get all sorts of interesting chemical reactions that could take place there. And hydrothermal vents are a place of abundant life on the bottom of Earth's oceans. So it's possible that those could exist at the bottom of Europa's ocean as well. Another energy source also could come from the surface. Europa's surface is bombarded by really high energy radiation, and this radiation can also make chemical reactions happen at the surface, creating perhaps interesting oxidants and organics that then, if they could work their way down through that ice layer into the ocean, they could also help be a food source. They could supply an energy source for life, basically. So we think Europa could have all the ingredients for life.
So this is super exciting. And, we think the ingredients are there. But Jenny, how is the spacecraft specifically designed to search for these ingredients?
Yeah, absolutely. It's a great question. So we have an incredible payload of instruments that are on board this spacecraft. We have 10 science investigations, and you can kind of see them here in the video being called out, all of the different instruments and investigations that are on board the spacecraft. And we kind of think of this payload almost like a really high-tech Swiss Army knife that's going to help us study, everything about Europa. So we don't have enough time to talk through, all 10 of these things in detail. But what I can say is that we kind of divide them into two groups. So we have a group of imagers, and these are instruments that will be taking images of the surface of Europa in a lot of different wavelengths of light. So of course we'll be taking high-resolution color imagery in the visible spectrum, but we'll also be taking images and data in the infrared and the ultraviolet. We also have a thermal imager, which is kind of a very high-tech pair of night vision goggles where we can see, places on the surface that are warmer, where maybe water has seeped up through the ice. So that's kind of our set of imagers. And then we have a set of experiments that are kind of fields and particles investigations. And so these are things that are going to be measuring things directly around the environment of the spacecraft. So we have a couple that are measuring gas and dust and other particles, things that may have gotten kicked off the surface of Europa and are kind of trapped in the gravity of, Europa's gravity field. We also have an ice penetrating radar that's going to look onto the interior of Europa and help us see the thickness of the ice and how much water is there. And then we have a set of instruments that are going to measure the plasma fields, the magnetic fields, and the gravity fields around Europa. And so understanding kind of that full picture of what's going on, not only inside of Europa and on the surface, but also in the environment around the moon, is going to help us characterize the moon in its entirety and help us understand if this is a place that is habitable.
This is amazing to hear. And, we're talking a lot about ingredients, but Cynthia, a question we always get is, will the spacecraft actually find life once it gets to Europa?
Yeah, that's kind of one of the key questions about this mission. And so the answer is a little bit complicated. So this is not a life detection mission per se. It's what we call a habitability mission. So basically our top level science goal is to explore Europa to understand its habitability. And so when I say habitability, I basically mean, are there places below Europa's surface that could support life as we know it? So are there, say, pockets of water within the ice shell that could support life? Or could the ocean itself support life? And so that's what Europa Clipper is going to do. It's going to look for those signs of habitability, those signs of places that could support life, that could have all of those ingredients. And then a future follow-up mission that actually touches the surface in some way, like a lander or something like that, you're really going to need a mission like that to do that life detection step. So to say, not just is Europa habitable, but is it inhabited? Is there life existing there today? You're going to have to land, you're going to have to, get some of that surface material or subsurface material onto some onboard experiments to really do that life detection step.
And, before Clipper can even make these observations, Jenny, I understand the spacecraft has to withstand a really punishing radiation environment at Jupiter. Can you tell us what it's going up against, and is Europa Clipper prepared?
Yeah, absolutely. So as you said, it's a really intense radiation environment there. Jupiter is a huge source of radiation, and it has massive magnetic fields that are trapping that radiation close to the planet. And yeah, you can see a really cool animation of that here. And Europa is orbiting within those magnetic fields inside of that kind of really, really intense radiation environment. And radiation and sensitive spacecraft electronics don't play nicely together. And so we've had to do a lot of preparation for this environment. It's one of the most intense places that you can send a spacecraft in our solar system. So we get at this a couple different ways. One is that we put a lot of our sensitive electronics inside what we call the vault. The vault is a piece of the spacecraft. It's basically a large cube that contains all of the spacecraft hard drives. The flight software is stored there, and a lot of the sensitive electrical components are inside of that vault. That vault has about 1/3 of an inch thick shielding. That's an aluminum zinc alloy shielding, and that really helps protect it from the radiation. Some radiation, of course, is going to get into parts of the spacecraft that aren't inside the vault, and some will still get through that shield. And we deal with that somewhat in software. So sometimes radiation can cause bit flips, so you can cause a 1 to turn into a 0 or vice versa. And so we can use software to actually detect when that happens and correct those errors as they happen. The other thing too is you can see, of course, the solar panels are not inside the vault. They're just hanging out there. So how do we protect things like that from radiation? And the short answer is we don't. We actually just kind of plan for it. We know, how much power the solar panels will produce, and we know that they'll degrade over time from the radiation at a certain rate. We have a lot of historical data that can help us understand how much these things will degrade over time. And so we just kind of plan for it. We know that that we will slowly lose power over the course of the mission, but that we have plenty of power to do our prime mission and then some, and to support all of the science we want to get at Europa.
And so both of you have touched on this a little bit, but it's worth driving home that Europa Clipper will not actually be landing on Europa. It will be orbiting Jupiter. Jenny, can you talk a little bit more about that?
Yeah, definitely. So yeah, as you said, we're not landing on Europa. This is an orbiting mission, although we do hope in the future that we'll send a spacecraft that will land on Europa and we'll get to actually, touch the surface itself. But we are going to be orbiting Jupiter and doing about 50 flybys of Europa. And we orbit Jupiter rather than Europa directly because of that radiation environment. We basically want to dip in, do a flyby, get a bunch of data around Europa, and then get out of there. And so we do that so that we can kind of extend the life of the mission and get as much science as we can doing those flybys of Europa. And so, those 50 flybys that we're going to be doing, that's going to give us kind of that global picture of Europa. We're going to be flying over lots of different parts of the surface and making sure that we can study this moon in its entirety.
Well, thank you both so much for that quick overview, but we already have so many questions pouring in online. It's actually pretty incredible. So let's jump right into this Q&A. And remember, if you're tuning in live right now, you can submit your own questions for Ginny and Cynthia using the hashtag AskNASA or by posting those questions into the comments wherever you're watching. So our first question is from Bruce on YouTube, who wants to know that since Europa is tidally locked to Jupiter, over time, wouldn't the oceans have shifted to the Jupiter-facing side of Europa instead of being uniformly spread around the moon? Cynthia?
That's a great question. So yes, so Europa is tidally locked. That means that one side of Europa always faces Jupiter and one side always faces away. And Europa orbits Jupiter about every 3.5 days approximately. So what we think, though, it's true that when Europa is closer to Jupiter, it gets tugged on, and that stretching and pulling produces tidal heating in the interior of the moon. And that's enough heating to keep this ocean liquid. So that's kind of the heat source that keeps this moon from just being frozen solid. It's this tidal heating, this tidal energy. But we think that the ocean is big enough, so it's global enough that heat is basically conducted, it's circulated through the ocean. So the ocean does stay as a whole global layer. It's not frozen on one side and liquid on the other side. Our evidence shows that it's actually a global frozen subsurface ocean layer, a liquid subsurface ocean layer.
That's great. And so we have a follow-up question from Brian on X, who wants to know, what specific data will the spacecraft be looking for at Europa? Jenny, you talked about that wonderful suite of instruments. Can you hit on this?
Yeah, absolutely. And Cynthia, feel free to jump in too if I leave anything out. But so we're going to be taking a lot of different types of data with the spacecraft. And it's really cool to me that, we're not landing on the surface, but we can still really get an incredible amount of information just from doing these successive flybys. So one of the most kind of clear, easiest to understand pieces of data that we're going to be taking is images. So we'll be taking a lot of images of the surface. And, when we take an image, it's not just a beautiful photo, although they will be kind of mind-blowing, beautiful photos, but we can actually study things like the shadows and, look at the different colorations and the different variations of things and learn a lot about the geology, why things look the way they do, just from looking at photos. So it's a really kind of incredible thing. And then, of course, when you take similar photos in different wavelengths of light, that will teach you about the composition of the surface. So, different different things will kind of react differently in different wavelengths of light, and so that'll give us a really good sense of what the surface is made of. With our radar instrument, we're going to be taking radargrams of the interior of Europa. So you could imagine kind of little X-ray goggles looking into the interior of the moon and getting a sense of how thick the ice is, how much water is there. Are there places where the ice is thinner? That will be complemented by our gravity experiment. That's going to be measuring the gravitational field. So we'll be understanding, the kind of gravity around Europa, places where the gravity might be slightly different. And again, that can help us understand what's going on inside of the moon as well. So those are kinds of things that we're, going to be looking at the moon from the outside, but we also have a whole bunch of spectroscopy instruments on board the spacecraft that's going to be tasting particles and gas and dust and things that are kind of above the surface of Europa. Some of those things may have actually been kicked off of the surface, and these instruments will be detecting them and tasting them and identifying kind of what these molecules are, and how fast they were moving and that kind of thing. So we have a whole huge variety of data that we're going to be taking when we get there that's really going to help us understand this moon.
Cynthia, do you have any follow-up?
No, great answer. I'm putting you on the
Okay,
science
great.
team, Jenny.
Well, I have a great follow-up for you, Cynthia. So, Jenny just broke down all the data holistically of what we're really trying to look for in this mission. But we have Rocket Man Randy on X who asks, what is the most promising indicator of life beneath the ice that you'll be searching for?
Yeah, so, we're not expecting there to be like multicellular, fish or anything in Europa's ocean. We're not going to complain if somehow, a fish gets thrown out and it, crashes into our spacecraft. We'll make sure we get some good pictures of it. But that's not what we're expecting to find here, right? So, most models of life on Europa, you're talking about like little tiny, like microscopic, single-celled kind of life forms. But even those would be super, super excited about. And so scientists have a lot of debates about what is a biosignature? What kind of measurement would you need to take to either detect life directly, or at least, tell you something about, clues that maybe there's life. And so the dust detector and gas detector that Jenny was just mentioning are two of our best ways to make kind of as direct measurements as we can of Europa from orbit, so from space. And so like Jenny was saying, there's going to be particles that are thrown off of the surface of Europa, either through micrometeorite impacts, that's like little bits of space dust, crashes into the surface, and it throws up bits of Europa's surface into space. There's also charged particles from all that radiation. Those also hit the surface, and they could throw some of the surface off into space. And so basically, those particles make a really, really thin atmosphere surrounding Europa that we think is made of kind of little bits of the surface. And so on our close flybys, like Jenny was saying, we'll be able to use our dust detector and our gas detector to actually suck in some of those particles. So we'll actually take those particles on board the spacecraft into our detectors, and we can study their chemistry. And so, because those particles they've been ejected off the surface in a pretty high energy event, things like DNA, if it existed somehow on the surface, it would probably get really, really fractured. And so we're not going to be able to detect like big, huge, complex organic molecules. But what we will be able to detect is kind of the building blocks as these particles get broken down as they hit our detectors. We can measure kind of the fundamental chemistry that they're made of. And so that, in my opinion, is going to be one of our best kind of clues, one of our best signs that, maybe there's something really interesting going on there that could help lead us toward thinking that there could be life there.
And I know you mentioned earlier, just to have a building block by itself doesn't necessarily mean that there's habitability. They all need to be like in context of each other. And so could you talk more about the bigger picture of how these individual observations can tell that bigger story that Clipper's trying to find?
So one of the really cool things about our instruments on Europa Clipper is that they're all designed to work together. So on some spacecraft previously, you had to fly by, and then if you wanted to take a picture with your camera, you have to rotate your spacecraft in one direction, and then to use the radar, you have to rotate it in a different direction. And so we made sure in Europa Clipper that all of our remote sensing instruments, all of those imagers that Jenny was talking about, they're all pointed in the same direction. So basically on each flyby during close approach, we don't have to pick. We can basically take observations of the same part of the surface with all of our instruments. And then at the same time, we're also collecting, the gas and the dust that are spewed off the surface. We're collecting those at the same time with our gas detector and our dust detector. We're taking those radar measurements, we're taking those gravity measurements, and those magnetic field measurements. So basically all of those are going to be taken simultaneously on each flyby. And so that's just really exciting because as a geologist, you get a lot of information from pictures. And I mean, I'm a pictures person. I love pictures of Europa, but being able to understand more about those pictures by having, the compositional information and then having the radar information to tell you the 3D structure and then having information about what was the magnetic field measurement right there as we flew by. It's really going to be the combination of all of these different instruments that's going to help us understand Europa. It's going to be fantastic.
Yeah, what an engineering marvel. Congratulations, Jenny, and to your team. And so we've been talking a little bit about images, and I know that's something that a lot of people are looking forward to. We have Antonio Gallo on X who asks, what will be the expected image resolution of the images that Clipper will provide? And what size of the objects on the surface will it be able to see? So essentially, how much is that surface visibility going to be for us? Jenny, I see you shaking your head. Do you want to do this one?
Yeah, I think I might actually toss it to Cynthia. I think I know the answer, but I think she'll know it for sure. So
yeah, so the highest resolution pictures we'll get will be at a resolution of about 0.5 meter per pixel. So that's about 1.5 foot. Okay. And so basically we'll be able to see things that are, like 3 feet across. And so, if there's a car driving around in Europa, we'll be able to see it really well. And yeah, I know it's crazy. And we'll also be able to use those pictures to get stereo. So not only will we'll be able to see kind of car-sized objects on the surface, but we'll also be able to see, how tall they are, what their sort of 3D structure is. And that's just going to be amazing.
And so I have a follow-up question. Honestly, maybe both of you could answer it. So we have a viewer on YouTube who asks, what considerations went into selecting Europa for this mission over the other potential targets like Titan or Ganymede? Do we want to take it from science or engineering?
Yeah, well, I'll at least start by saying that I want to go to all of these places. So I think it's just a matter of, when we get to go, right? So we're going to Europa now, which is incredible, and there's so much we're going to learn there. It is, of course, kind of one of our most promising places in the solar system to look for a habitable environment. We have, other missions that are being planned to these other bodies. Of course, there's a lot of excitement about Enceladus, too, a moon of Saturn that is also kind of an icy ocean world. So, just from a totally selfish perspective, I want to go to all of these places. So let's go.
Yeah, I'm totally with you. Just, build me a couple more Europa Clippers, Jenny, and we'll send them everywhere. That's right. The reason why, and one of the reasons why Europa was chosen to be kind of the next flagship destination was that coming out of the Galileo mission. So that was a mission in the late 1990s that studied Jupiter, the Jupiter system and its moons, including Europa. That was really when we sort of started this whole revelation of the idea of an ocean world, the idea that an ocean could exist out in the outer solar system beyond the Earth. And that really it expanded our whole idea of the habitable zone. We used to think that, to be habitable, to be a place where life could live, you had to have liquid water stable at the surface. And so you get into this kind of Goldilocks story where in our solar system, Venus is too hot and Mars is cold and Earth is kind of just right. And so discovering that worlds like Europa could have oceans. Europa is kind of like the type example. It's kind of like the OG ocean world. Out in the outer solar system, here's this ice layer at the top, but then there's this huge liquid water ocean. And so really, we've been working on planning this mission for 25 years now. We've been talking about it. And then finally, about 9 years ago, we got the new start, which is when you sort of get the rubber stamp from NASA headquarters to say, okay, this mission's real. Let's go ahead and figure out how to do it. So yeah, but the other locations too, NASA's also working on the Dragonfly mission, which is going to go and explore Titan. That's an octocopter that's actually going to fly around in Titan's thick atmosphere. So that's going to be amazing. And in the latest the National Academies of Science put out a decadal survey every 10 years. And so they ranked an Enceladus mission called the Enceladus Orbilander as kind of the next big sort of ocean world flagship mission as well. So yeah, we're really excited to see exploration of all of those places.
And we'd be remiss too to not mention the JUICE spacecraft. JUICE launched last year. This is the Jupiter Icy Moons Explorer mission, and it's going to get there kind of around the same time that Europa Clipper will. And this is a mission put on by the European Space Agency, and it's going to be studying the icy moons of Jupiter in general, but we'll be focusing on Ganymede, which I know our viewer asked about. So NASA's not the only one sending spacecraft to these incredible worlds too. So yeah.
Thanks for mentioning that, Jenny. And as we are full steam ahead on Europa right now, we've got Thrash Munster on YouTube who wants to know, for both of you, what do you hope to discover or uncover during your research on Europa? Jenny, we'll start with you.
So, yeah. Okay, good.
Oh, yeah. Oh, man. I mean, it's such a hard question, right? I mean, it's a basic question, but it's a hard one because there's so much that we want to know about. For me personally, I mean, I'm really excited about the water, understanding how much water there is, kind of knowing, as much as we can about it. How salty is it? Is it uniform underneath the ice? And just kind of getting a sense of what that water is like. As Cynthia was mentioning, this kind of class of bodies, these icy ocean worlds, we're seeing that they could be quite likely to be abundant in different parts of not only our solar system but in the universe. And so being able to study one up close with this incredible spacecraft, and just really understanding more about the water that's there, the fact that there could be twice as much water there than there is on the Earth, and I think of the Earth as a place that has quite a lot of water actually, and so the fact that there's a place in our solar system that's smaller than the Earth that with twice as much water, I mean, that blows my mind. So for me, understanding more about the water is really what gets me excited.
Yeah, and really for me, it's the pictures. I can't wait to get those high resolution pictures of the surface. I want to see those cars, or there's those car-sized chunks of ice on the surface. We don't think there's actually cars. But, just getting to see the surface, it's going to be 12 times better resolution than anything we've seen before from Galileo. So I think we're just going to be completely surprised and stunned at, how different the surface looks. And as a scientist, that's the best thing, right? You want to be surprised. You want to see something that nobody predicted you'd see there, because that's where the science is, right? That's where the excitement is. So I just can't wait.
And Jenny, Skate Screams on Twitch asks, what do you expect to find in respect to the magnetic field? You were talking about that huge magnetic field around Jupiter. So what would be ideal in results for you?
Yeah, so one of the questions we get a lot is basically like, how do we know the ocean's there, right? I mean, we can't see it; it's underneath the surface. So how do we know an ocean is there? And what's really incredible is that the Galileo spacecraft that kind of discovered the ocean, the way it discovered it was through studying the magnetic fields. So the magnetometer instrument on Galileo was able to characterize the magnetic fields around Jupiter and how they interact with Europa, and basically found that the way the magnetic fields would look the way they do is if there was some sort of conductive layer underneath the surface. And what made the most sense for kind of all of our research and modeling is that this is a layer that is salty and able to conduct some of that magnetism. And so studying the magnetic fields might just seem like, oh, we just want to understand more about them, or, kind of have a sense of how they change over time. But really what it's helping us do is understand the interior structure of Europa, which kind of blows my mind, that we can make that inference, we can make that jump from studying magnetism in the Jupiter environment and in the Europa environment, and, from that able to infer that we have this conductive liquid layer underneath the surface. Is just kind of mind-blowing.
Yeah, no, this all blows my mind. I mean, really, to think about everything that we can learn and study from so far away, it is just really incredible what teams can come together and do. And so I'm going to pause for 2 seconds right here. We still have a ton of questions pouring in online. But before we get to the next one, I actually have a question for our viewers. If you can ask the Europa Clipper spacecraft one question when it arrives to Europa, what would it be? Drop your question into the chat box wherever you're watching. Alrighty, let's get to the next Ask NASA question. So we have, this is a great question. We've talked about what Europa is going to do, Europa Clipper is going to do when it gets to Europa, but we haven't talked a lot about that big journey it has to get there. And so we have Project H on YouTube who wants to know, how much fuel does it take to get to Europa?
Yeah, absolutely. I can definitely take that one. So our spacecraft has about 6,000 pounds of propellant on board. That's about half of the total mass of the spacecraft. So it's a huge amount of fuel. If you're looking at a picture of our spacecraft, the kind of center piece where everything is mounted, most of the interior of that is 2 giant propulsion tanks that are filled with propellant. So that 6,000 pounds of fuel, though, is mostly used to make attitude adjustments, so to change which way the spacecraft is pointed, but also to change our trajectory. And, as we kind of are flying around Jupiter, flying past Europa, we will use that propellant to, help change things and help make sure that Europa is staying right in line where it needs to be, right, on its path. The actual journey from Earth out to Jupiter, so much of that speed is actually gotten from the launch itself. So when we launch off the surface of the Earth, we get a huge boost from our Falcon Heavy rocket that gets us going really, really fast. The Falcon Heavy is a massive rocket, so it gets us a lot of speed. And then we actually are going to pick up a little bit of a kick from doing a Mars gravity assist and an Earth gravity assist. So we'll pick up a little extra speed from doing flybys of those 2 planets. And then we get going just really, really fast all the way out to Jupiter. And this should hammer home just how far away Jupiter is, that even with all of that speed from the launch and the 2 gravity assists, it's still going to take us about 5.5 years to get out to the system. So we have to be patient. Of course, it'll be worth the wait, but it is quite a long trip out there.
And I have a great follow-up for you, Ginny, from Mikey Wasabi on YouTube. Considering how far away it is, how long will it take for the images to transmit back to Earth?
Yeah, that's a great question. Oh gosh, I'm going to get this wrong, but maybe Cynthia remembers our one-way light time. I believe it's about 45 minutes, so an hour and a half round trip. Is that right, Cynthia? Okay.
Yeah, about that.
So it takes about 45 minutes for light to go from Jupiter to the Earth and vice versa. So if we send an image from Jupiter, it'll take 45 minutes for it to get here. And then those images have to get processed on the ground, and certain things have to happen. But we do release kind of all of that data pretty quickly out to the public, kind of as soon as we can. And so, so it takes a long time for light to travel just between, again, the 2 planets, which should give you a sense of just how far away Jupiter is.
Yeah. Wow. Thank you, Ginny. Our next question is from Titan on X, who asks, how will Europa Clipper detect potential chemical or biological activity in Europa's subsurface ocean? Do we want to take this on science?
Yeah, I can take that.
Okay.
Yeah. So that's a great question. So a couple different ways. One of the things you can use is that magnetometer that Jenny was talking about. When you measure the magnetic signature of Europa, one of the parameters you get like the strength of the field, you get the direction, but you can also use that field strength to tell you something about the salinity of the ocean. And so salinity means how salty it is. And so we think from our models that Europa's ocean is a salty ocean, and we think it's a little bit less salty than Earth's oceans. And so we'll be able to get more information from those magnetic field measurements. But then another really cool measurement we'll be able to do is we can use our near-infrared mapping spectrometer. So this is an instrument called MISE, and basically it takes pictures of the surface, but rather than just like, in red, green, and blue, it uses multiple wavelengths in the near-infrared. And those wavelengths are really diagnostic to there's absorptions that are based on different chemicals on the surface. And so we know from some of our preliminary data that we got from the Galileo spacecraft that a lot of the dark stuff, like that you're seeing in these pictures here, there's kind of this dark iceberg-like terrain, and then there's the dark kind of streaks along the surface that we know now are cracks and ridges. And those geologic features they're associated with places where we see more of this kind of non-ice material. Most of the surface, like the stuff that looks blue in this picture, that's mostly pretty pure water ice. But all of kind of the reddish, brownish stuff, those are places where there's higher concentrations of these non-ice materials on the surface. And so we think from our initial observations from Galileo, 25 years ago now, that we're talking about highly hydrated things like magnesium sulfate or sulfuric acid, but we just don't know for sure. And so the measurements that we'll get from this compositional imager will be able to give us just much more detailed information about the chemical compounds on the surface. And we think because they're associated with certain kinds of geologic features, like these cracks and like these disrupted areas, that those are places where material from the ocean has actually come up through the ice layer onto the surface. And so that's another way that we can kind of use our clue of our surface observations to tell us something about the composition of that deep subsurface ocean.
And as you were giving this explanation, Cynthia, we had some really beautiful images of Europa popping up on the screen. Can you remind us, so you said we're getting, about a half a meter resolution? Like, what is the difference between those images we are seeing, which already look pretty incredible, to what we can expect for Clipper?
Yeah, so we have one high-resolution picture of Europa that was taken from the Galileo spacecraft. The highest resolution picture was at 6 meters per pixel, but we only have one picture at that resolution, like just one little tiny postage stamp on the surface. And so here you're seeing some kind of global scale images from various spacecraft, but really the best we could do with Galileo was that single 6 meter per pixel image. And with Europa Clipper, we'll get images over almost 90% of the surface at a resolution of about 100 meters per pixel. So that's going to be amazing. We're going to be able to see, house-sized objects, no problem on the surface with this. And then we'll get images over some portions of the surface, so less than 90% at this half a meter per pixel. So that's 12 times better than the best high-resolution picture we saw from Galileo. So it's just going to be amazing.
I cannot wait.
It's amazing to think that, we these are real photos that were taken by real spacecraft, right? And when I look at that picture from Voyager and then compare it to Galileo, the Voyager picture, it's like, oh, wow, cool. There's this dark region. And then you look at the Galileo ones and it's like, oh, that was actually 4 or 5 different types of terrain in that dark region. And it just, kind of looked all the same. And then we get these higher resolution images and then suddenly it just completely changes our understanding of what we're looking at. And so to think that Europa Clipper is then going to do that again, like an order of magnitude, better images, it's really, really cool.
I have another great follow-up question. We're on the photo stream today. So we have Squid on Twitch who asks, who decides what pictures get released to the public and what is the criteria on that?
That's a tricky question that has an easy answer, which is everything gets released to the public. This is a NASA-funded spacecraft. This is paid for by your tax dollars. So thank you, everyone, for funding Europa Clipper. And in return, we're going to give you pictures. So basically, all of the pictures that are taken after some very sort of initial processing we're going to post them all up on a photo archive. We've done this for other missions, like with Cassini and like with the Mars missions. And so, yeah, pretty soon after they're taken, there's just going to be a stream of pictures. You can go there every day and, look at what the new images are. And then we'll do some so those are called raw images. So basically that's just, it comes off the spacecraft. We do a little bit initial processing to turn it from like digital bytes into an actual picture you can see, and then bloop, it'll go right up on the website. But then we're also going to do some more complicated images when we see something cool. And so that'll be, our pictures some of them are going to be like a bunch of little squares, but it's much more easy to understand what's going on if you stick those all together into an image mosaic, or if you put together the different individual color bands to make a color picture, or if you combine information from the camera with information from one of those compositional imagers. And so those kind of like combined science products, those are going to be done with the different instrument teams working together, and those will be released when we have something cool to show. But yeah, so all the raw data will just be out there for people to see.
And so, in terms of this data collection, we've got another viewer on Twitch who wants to know, when can the public see your results? As we're doing these flybys, is it going to be instantaneous? Jenny, how about you take this one?
Yeah. Sure. So yeah, I mean, we talked a little bit about how the one-way light time is 45 minutes. So, even the minute the camera snaps a photo, we don't get to see it even for a little while until that data, comes down. And even then, we have to store it on board, and then the data gets downlinked a little bit later. So there is kind of some processing time. We don't quite get like, live video feed from Europa. And then there's processing on the ground. And so, but we do try to release stuff basically as quick as we can, as soon as we get the data and can send it out to the public. And then, of course, there's kind of the bigger question of like, when will we have results, right? We may have the raw data, but when do we actually have can we draw some scientific conclusions? Obviously, that's a little bit harder to determine. It depends on what the question is that we're asking, who's doing the research, and do we have all of the data needed to answer those questions. So that might take years and years as those kind of scientific papers come out over time.
So we know that the images are available to the public, but is the data available as well?
Yeah, so one of the requirements for any NASA mission is that all of the data gets put into something called the Planetary data system. And that's a free archive of scientific data from all of the NASA missions. And so, a mission like Europa Clipper, there's basically a period of time where you downlink the data, and then each of the investigation teams gets some time to, make sure that the data, that they understand all of the processing, that they understand what the data is showing, that there aren't any, mistakes or weirdnesses in it. And then once the data has been validated by the teams, then it's archived into this Planetary data system. So the pictures are special in that just the raw images from those will be put online. But all of the data from the other instruments, it will be put into the Planetary data system. There's often a delay of about, 6 months to a year. I don't know, Jenny, if you remember the data archiving plan, exactly when, say, the first batch of data goes in.
Yeah, that's about right. It does take a little bit of time for all that kind of processing and validation to be done. But the Planetary data system, something you can go Google and it will pop up. This is a thing that is publicly accessible, and all of our data will end up there.
Very cool. So Cynthia, I know you mentioned that you are a geologist, but I know that you are also an astrobiologist. And so I have a very good planetary protection question for you. It is from Mad Perma on Twitch, who asks, do you think there is a possibility that we bring along some microorganisms from Earth that could find a new home on Europa?
Yeah, that's a really important thing that NASA has to be very careful of. So, because we think Europa could be a place with life, the last thing we want to do is, kind of like destroy or infect that life in the process of trying to detect it. And so NASA has a planetary protection office, and their job is basically to protect, different places in the solar system, so moons and planets, from contamination from the Earth, and also the reverse contamination, where if we bring pieces of, say, Mars or the moon or another place back back from there to the Earth, we also want to make sure that we don't contaminate Earth with any of those materials. In the case of Europa, we're not going to bring anything back, so we don't have to worry about that. But we do have to make sure that we sterilize the spacecraft. And so that's something we've had to be very, very careful about, is we built the spacecraft in a clean room at JPL. And if you remember in the video, so here you can see, here's the spacecraft in one of our clean rooms, and you can see how everyone in there is wearing what we call a bunny suit. And these are suits that basically cover your whole body, and you're wearing gloves and a mask. And you're basically making sure that, you don't sneeze on the spacecraft, right? You don't get little bits of skin or hair or anything stuck on it. And then all of the instruments, you can see how they're wrapped up in this kind of protective shielding. And then people are just very, very careful. And then the folks here, one of the things they do is they actually, they swab the spacecraft as well. So once the spacecraft was built, we had contamination control engineers that went in, and they basically took samples of every part of the spacecraft that they could get, their little swabs on, and then they cultured those in a laboratory. And that was basically because, you can never have a spacecraft that's 100% sterile. And so they wanted to know for sure, what are the microorganisms that we're bringing along with us, so that if somehow we detect something when we get there, we know, oh yeah, that was just, we probably just brought that with us if we find, E. coli or some kind of bacteria there. And one good thing about the spacecraft too is that, one good thing about that radiation is that a lot of that radiation that's helping, it kind of threatens the survivability of our spacecraft. But one good thing about it is that it also sterilizes the spacecraft. So most of the outer parts of the spacecraft, they're going to get, a nice high dose of radiation. And so if there's any little microbes that were hitching a ride on the outside, probably they'll have been baked off, before we get to Europa. So.
Oh, so cool. Thank you for explaining that. I mean, to see the inside of the clean room and just behind the scenes of everything that goes into doing a mission like this, it's almost like a movie, it's very cool to think about. And so I have another question, that hits on this topic of doing what has never been done. Is Even Vital on X wants to know, are there any technologies that are being used in the instruments of Europa Clipper to optimize the detection of these key molecules? Jenny?
Yeah, absolutely. So we have 2 instruments on the spacecraft that are kind of specifically designed to look for particles, gas, dust, and that's our mass specs instrument and our SUDA instrument. So that's our mass spectrometer and our dust detector. And these are some of the most advanced versions of these kinds of instruments that have ever been flown in space. They've, maybe had kind of predecessor instruments, older versions of the instruments that have flown on previous spacecraft. And so these are some of the most advanced forms of, a spectrometer and a dust detector that have ever been flown in space, and we're bringing them with us to Europa. So, the technology that flies in space is a little bit different than technology that we might have kind of in a laboratory. And that's because our spacecraft hardware needs to be radiation hardened. It needs to be able to survive kind of crazy thermal environments as we, fly out to Jupiter, and kind of the difference in temperatures that you get from when you're in the sun versus when you're in the shade. And so the spacecraft, the hardware that we fly on spacecraft has to be very specially designed for that kind of environment. But fortunately, we're bringing both mass specs and SUDA along to detect these kinds of particles that are going to be in the environment around the spacecraft.
So cool. And Jenny, I've got a great follow-up for you. It is Benjamin on YouTube who wants to know, will it be possible to orbit in the projected path of water geysers as an opportunity to get as close to a chance to study what's under the ice from above it? So, flying through these potential geysers and
Exactly. So there is some evidence that there may be plumes. We call them plumes, but geysers is also a good word. There is some evidence that we may have plumes on Europa. And so, of course, there's a lot of interest in, could we fly right through one and, directly sample some of that water? It will be kind of hard to predict, where those plumes are going to be. And, maneuvering the spacecraft to fly right through one is a very challenging thing. And of course, our trajectory has been planned out out kind of well in advance. But that is exactly, what the viewer asked, that if we were able to sample some of that water from a plume, that would be water that's coming from underneath the ice, right? So it's kind of a direct measurement of some of the water. I don't know, Cynthia, if you want to add anything to that.
Yeah, and so one of the cool things is that our mass spectrometer and our dust detector, like Jenny was mentioning, they're really, really sensitive. So even if there are no plumes erupting, we'll still be able to measure just those very few particles that get thrown off the surface through those micrometeorite and other impacts. But if there's a plume, we'll get 100 times or more sample. We'll get a huge amount of material, and so we'll be able to make even better measurements with those instruments. So yeah, being able to fly through a plume is kind of like a stretch goal, right? We don't have to do it, but if we could, it'd be really cool.
Amazing. Yeah. Yes. And so, Cynthia, we have James White on YouTube who asks, as we are saying water throughout this show, are we meaning that it's H2O or is it just a liquid?
Yeah, so we're actually talking about liquid water. The same H2O that we have here in Earth's oceans is the same water that's out in the outer solar system. So yeah, an ocean of liquid water, liquid H2O with some salt in it. And the salt could be things like this, magnesium sulfate, which is like Epsom salt. So, we have that here on Earth, or it could even be sodium chloride, which is the same, table salt that we have here on Earth as well. So yeah, these are familiar materials in a really unfamiliar location.
Which is just it's still mind-blowing to think that, one, this exists, and two, that we are on our way to study it. And I have a follow-up question. I'm not sure if it's a science question or engineering question, but we'll start with science. And Cynthia, toss it to Ginny if you think that'll be better. But we have Sammy Connor on YouTube who wants to know, how thick does the ice need to be to protect potential life against radiation from Jupiter's magnetic field?
So it turns out that ice is actually a pretty good protector. It's a pretty good insulator from radiation. So you only need about 10 centimeters of ice. So, that's only a couple inches to get down below a lot of the radiation. And if you could go down as much as, a foot or two, then you'd really be pretty safe. So a future follow-up mission that might land on the surface of Europa, if it's going to be trying to do a direct search for life, what you'd really want to do is not just, you'd want to land, but then you'd want to dig down below that, what we call the radiation processing depth. So you'd want to dig down into a kind of a fresher, more protected depth, but again, you don't have to dig that deep. And then you could get some of this fresh material that hasn't been as fried by radiation.
Yeah, and what's cool is, so we only have, you were saying that, ice is a really good protector, right, against radiation, and 10 centimeters or a foot down, well, the ice on Europa is miles thick, right? We are kind of, our best estimates is that we might have an average of maybe 10 to 15 miles of ice on the surface. Great. So, yeah, which is, a really thick kind of protective layer. And so, we were talking earlier about how the radiation environment is kind of good to sterilize the spacecraft, right? If we brought any little microorganisms along with us, it's a good thing to kind of, keep our spacecraft clean. But that doesn't mean that life can't exist in that environment. That's what's amazing about Europa, is that underneath that ice, because it's such a good protective layer, there's a really good, potential for a habitable environment.
So we have just a minute left, but could you both briefly answer this question from Ian Carter on X, who wants to know what one finding would make this mission totally worthwhile for you? We'll start with you, Cynthia.
Finding a fish, finding some kind of macroscopic life form. That would totally make it worth it. But honestly, just getting that first super high resolution picture of Europa at, 12 times better than anything we've ever seen before, that's going to be kind of my, okay, we've made it. There's my picture. Anything else, but, and we're going to get hundreds of those pictures too, but it's going to be that first one where I'm just going to be so excited.
Yeah, and for me, I think it's, I keep talking about the water and how much that excites me. I think, we have a really good understanding that there should be water there. There, we like kind of all of our research and models point to that, but getting confirmation that yes, there is an ocean and kind of here's how much of it, when I think about other bodies in the solar system, the moon and Mars have kind of ice at in the polar regions, kind of frozen and water in certain places. Of course, Earth has an abundance of water, but the fact that there's another place in our solar system that in such a harsh environment, but that could have this liquid water ocean underneath the surface is just, again, every time I think about it, I get chills, and it's kind of mind blowing. And so getting the data back that says, yes, there's water and here's how much, that's going to be the thing that will make it all worthwhile for me.
Well, unfortunately, that is all the time we had for today. But this has been such a great show. Cynthia and Jenny, thank you for taking so many questions from our viewers, and good luck on that launch.
Thank you so much. It's going to be amazing
Thank
next
you,
week.
Tahira.
Make sure you watch.
Yeah, it's going to be awesome.
Yes.
Thanks so much for having us today.
And thank you to everyone who joined us online. We had some really fantastic questions today, and we just love getting to engage with you live like this. Now, hey, before you go, we actually have a special opportunity for you to have some fun with this mission before launch. You can join NASA's Runway to Jupiter Challenge, where you can create and share your own cosmic looks inspired by Jupiter and Europa. You can learn more at go.nasa.gov/runway to Jupiter. Now, we hope you enjoyed learning more about the Europa Clipper mission, and remember to join us for the launch of the spacecraft. That launch window opens on October 10th from NASA's Kennedy Space Center. You can watch it from home in both English and Spanish on our free streaming platform, NASA Plus, or across any of NASA's digital channels. You can also stay updated on the mission by following NASA Solar System on Facebook, X, and Instagram. Thank you all, and see you next time.